Okay. Now, so this is what I wait. You weren't here in the morning. So this, or maybe you. So this was actually exactly the reconstruction of the board from earlier today. So this is the. I just feel that I'll spend most of the talk reminding things that already happened here, but quite a lot of things happened, so I don't feel bad about it.
But can I just say what is your plan? I mean, what do you
So my plan is to explain the outline of the proof, the plan of the proof, I guess. We cannot really say it's a proof, of the Geometric Langlands Conjecture. And the main idea is to use this diagram. In other words, the point is to approach, it works on both sides, but let's talk on automorphic side, to compute automorphic forms via their Whittaker coefficients, which is a very natural idea. So we identify them by these Whittaker coefficients, which the unpleasant fact is that we have to somehow work differently with non-zero coefficients and with zero coefficients. So this is the reason why we split this category into, we think of this as a gluon of two categories. There's an interesting gluon functor that allows us to recover the category upstairs from the bottom line, but it's not important at the moment.
Zero non-zero is the index of the non-zero coefficients.
Yes, so it's the coefficients with the zero index and the coefficients with the non-zero index. Right.
What's missing in the picture is the Kac-Moody and the operators. Where are they?
So they are tools we use to match the two pictures. So this, so in other words, I didn't want to put it on the diagram. I think it will be too messy. But we have ways of just putting things in here. And similar ways of putting things on the Galois side, which I didn't have time to draw yet. And the idea is to put things in here and then make sure that they match by looking at their Whittaker coefficients. Now, because I'm going to, as I mentioned, look at Whittaker coefficients separately, the zero and non-zero, I wanted to talk about the various functors relating these two categories, three categories, sorry. And there are two functors already on this diagram, the non-zero Whittaker coefficient and the zero coefficient, which can also be called the constant term. And they all both have adjoint functors that can be thought of as some kind of series, Eisenstein series on one side and Poincaré series on the other side. For our purposes, this Eisenstein series is maybe the more important one, because this is one of the two ways to generate things here. The other one being Opers and Kazhdan-Lusztig. Well, Opers/Kazhdan-Lusztig.
Looks like everything that you have on the board looks classical.
That's correct. So, well, I guess the gluon functor not here, but yes, this story is classical. And in fact, as I said, there will be two ways to generate objects here, and one of those ways is classical, the Eisenstein series. So that's why I want to say that we'll use this Oper/Kazhdan-Lusztig story is used as a way of, it's our way of dealing with Caspidal story. So, and that's the non-classical part. Any other questions? All right, so let me now tell you what happens on the Galois side. So this, I'll shorten it to G. So the counterpart of this diagram was somehow, I guess, one of the points of my lecture on gluon. So there's our object of study, the category of incoherent sheaves with nilpotent support on the stack of local systems. I'll just write ls for local systems, otherwise it will never fit. And you can say that it embeds, it's a theorem, that it embeds into a certain glued category, but this glued category is somehow, so the extra piece of information that we use is, the only thing that we use somehow geometrically is a projection map from local systems on G check to local systems on B check. And remember, I'm assuming that my group is GL2, so I don't have to worry about other kinds of parabolic. I guess I was denoting it by P spec. One way or the other. To keep with the spirit of this workshop, I should write it like this and then say, Braverman, which way does the map go? But apparently I cannot answer this question. OK, so, and this was defined to be the gluing of the following two categories. So on the one side, there's the category of quasi-coherent sheaves on just downstairs. And on the other side, there's a category of quasi-coherent sheaves upstairs, but with an extra piece of data. So it's quasi-coherent sheaves upstairs that are somehow horizontal along the fibers of this map. So they carry a connection along the fibers. And in this case, the gluing functor is essentially just pulled back under this morphism. And so the category, this extended spectral Whittaker category, was just defined as the gluing. So I don't want to talk about it much because it somehow doesn't seems like purely an artificial object to make the, well, to compare the two stories. All right, so this is the counterpart of the first diagram. But I think it's also makes sense to look at the counterpart of this series and coefficients. So this is the series and coefficients on the A side, on the automorphic side. There's also the series and coefficients on the Galois side, where what are the relevant categories now? So there's our favorite category of incoherent sheaves with nilpotent support, singular support. There's the quasi-coherent, its quasi-coherent counterpart, and the category with somehow move them so that there's more room. So and then there's the category of horizontal, of quasi-coherent sheaves upstairs with connection along the fibers of P-spec. So this No, but I'm not done with the. It's the same because I didn't draw any arrows yet. I'm paying particular attention to the arrows. So now here comes the arrows. And you can, of course, formally call them just some kind of Galois or spectral counterparts of the maps written of this automorphic part. So this is Unfortunately, I think Dennis used it for something more subtle. So fortunately, I will not use this map much, so we can ignore. Hopefully, there will be no confusion with this notation. So I can call them the same way. But they, on the spectral side, they also have some clear description. For example, this map from these two maps between quasi-coherent sheaves and incoherent sheaves are the standard maps relating the two categories. There's an embed in one way. This is
It's just embedding.
what?
It's not.
Wait, I think I'm saying something strange. No, I don't think so. Yeah, so it's fully faithful. And there's psi in the opposite direction, while these two maps, one of them is, I don't know, can you still see what every symbol refers to? Is the diagram getting too messy? Okay, so this map is a kind of push forward under this map. The only difference is that because our objects have connections along the fibers, this is closer to the RAM push forward than to usual push forward. So this is, maybe I can denote it like this. So this is, and this map, this map is essentially pullback, but composed with psi. Anyway, all of those maps can be described explicitly, and because everything here, the only difficulty on the Galois side is that things are, so we're thinking this incoherent world. Sometimes we might also need to think in DG terms, but there are no infinities involved anywhere. So it's all very, and it's not that far from some classical algebra geometric questions.
So now I'm confused about layout. So circled map.
Circled maps are just the definition of the.
Lowest Nabla is just the same as Eisenstein.
Yes. So this is, I don't remember if you were here in the morning. So there was this discussion why this even deserves the name of Eisenstein series. Well, this is the left adjoint, so this is the lower Schrick Eisenstein series, and this is not your usual Eisenstein. So the usual Eisenstein series starts at band T. This starts at some other category, which somehow cooked up. It's band T with some changed gluon. I mean, this is somehow the definition of this, was to change band T to make it as close to band G as possible, while still somehow retaining its nature. So this is, and all normal Eisenstein series functors, say compactified and usual Eisenstein series functor, they factor through this one. So this is somehow the most fundamental Eisenstein series functor from this point of view.
And all four maps going up to here to there are fully faithful.
So this is the, from where?
So there are two maps going up, and on the right two maps going up, and they're fully faithful.
Well, this one is not supposed to be fully faithful. So because this one involves somehow integration along the fibers, so it will be fully faithful for, I mean, this.
Is the idea of the proof that you have these items at the bottom, you look them up, you...
No, the idea of the proof is really to generate things upstairs and use the fact that, well, this is not fully faithful, this is not fully faithful, but together when they're glued, they are fully faithful. So we don't actually talk much about, I mean, So the Eisenstein series map is used to generate objects here, but the idea is really just generate objects and look at their and compare, make sure that their images match. Any other questions?
On the right-hand side, are you saying that spectral constant term is a thing circle? To the right? Is that
Is the order, is something wrong with my direction of arrows?
composed with the upper shape?
No, that's somehow, no, that's the point.
That's what you're saying?
Uh,
Not what you're saying.
So if it's this constant term is p upper shrik composed with psi. So you apply p first and then you put it. So this is an int-coherent sheaf downstairs. You lift it, you get an int-coherent sheaf with a connection, and then you make it into a quasi-coherent sheaf. This is what it's. I believe this is what it says. So what?
Where does psi land? Sorry, phi.
That's spec. Oh, that's. Oh, psi. This thing. This thing.
Yeah.
This is the natural functor from int-coherent to quasi-coherent. So this is the. So if you think of quasi-coherent as some support condition, this is the functor of sections with support.
Yeah. Okay. Maybe
Yes.
I'm stupid, but doesn't the arrow end?
In quasi-coherent.
Yeah, but over. Okay, that's fine. Maybe I was just confused. That's all right.
No, but it's like you have an int-coherent sheaf with a connection after first functor, and then you apply psi to turn it into a quasi-coherent sheaf with a connection.
Oh, it's sort of. Oh, it's a psi relative to. It's psi with connection. It's not the same psi as on the left-hand side of the diagram.
No.
It's psi with
And
connection.
yes, it's absolutely no, well, I mean, this is like psi on LSG,
Yeah, it's psi.
and this is psi on LSB.
In which case they need different notations.
Technically, but I mean, in the paper there is usually a subscript, but I don't know. Maybe I just find the amount of subscripts overwhelming. Okay. Any other questions?
That equivalent support condition here, so the result land there naturally, or you impose it
For which one? For this one?
for Eisenstein?
For Eisenstein series this way, no, yeah, it appears automatically. So this is, in fact, this is one way to guess this. This is like the smallest support that will include the image in this. Okay, so now, as was promised, I'm going to generate a bunch of objects in those categories. So this is the second part of the story. I no longer need this diagram. I'm going to keep this one, though. So part 2, generators. And there are, on both sides, we produce two families of generators, two types. So two types of them. First of all, there are the Eisenstein series. And by this I mean, so these are reasonably classical. I mean, we, at least on the automorphic side. And on the automorphic side, so we look at the, well, just look at the images of the corresponding Eisenstein series functors. So there's Is of WGB. D mod of 1G. And on the Galois side, well, really, I shouldn't be saying, I guess I can consider image. It doesn't matter whether I generate a category, right, or not. So the image of the corresponding spectral, this. Just consider this map. And let me also just use this notation. So I just find that this never fits anywhere. So since this is I'll denote it by the same symbol as the category of constant terms. So this is like the spectral category of constant terms. This is one way to put it. Okay, so this is the first class of generators, and they are indeed somehow more classical, except for the fact that we consider this strange source, and they are somehow the methods of dealing with them are relatively classic. So this is the first class of generators, and the second one, I'm wasteful of the board space. So the second class of generators, I guess, yeah. So these are the operas. So on one side it's more natural, on the Galois side it's more natural to think of them as operas. On the automorphic side you can think of them as localization of this Kazhdan-Lustick category. So now you all heard what operas are. I want to say, well, you all heard what operas were. So, and just short summary, I mean, this is the way I think maybe easier to remember. So operas are to G bundles. So this is one of those SAT things. Operas are to G bundles as differential equations of order n are to systems of n differential equations of first order. So this is like a, oops, sorry, I didn't mean to strike this out. So this is a neat way to keep in mind what these objects are all about. And this also should tell you that, like many other things in this story, this is what happens for GLN. For GLN, the story is much simpler and more classical than for arbitrary group.
Is it G bundles with connection or just?
Yeah, G bundles. Operas are to G bundles with connections. Thank you. All right, and so, and as I said, these are, we'll use them as a tool of dealing with, of somehow complementing the Eisenstein series. That Eisenstein series don't cover everything. This is somehow whatever needs to be covered is called cuspidal, and these will be enough to produce cuspidal, to generate cuspidal category. So, Dennis, I wanted to make sure the notation is consistent. Maybe he can check when. So I would prefer to work with global operas rather than with local operas, and I think he was dealing with int, so it's better to supposed to work with int core rather than with quasi-core. So it's some global unramified operas, and I need to fix something. So actually, somehow maybe the most explicit way of doing it would be to fix the type of singularities that I allow these operas to have. Then they will form somehow a reasonable space. And but then I have to consider the union of those spaces for all possible types of singularities, but that's okay. So on the automorphic side, I consider this functor. This is the Kazhdan-Lustig localization into d mod of bond G, and just take its image and again somehow this is not really a single object. You can either think about it as a bunch of local things, or you can think about it as global things, but then you have it's probably better to consider different singularity types separately. So maybe if this can also be thought of as some kind of quantized Hitchin vibration, but I don't think these words appeared, so probably I shouldn't use them. So anyway, so there is a functor here. In the notes, this one, Kazhdan-Lustig, is used for the local picture. This one is called the quantized Hitchin vibration. So just so that you know. And on the Galois side, on the Galois side, there's simply a map from operas to local systems. And we can just take the image, again, take the image of the push forward functor. So take image of, I think this map was denoted by V. So this will be V lower star, or more precisely, this is V lower star. And then I think if I deal with int core, that's so image of V lower star. So I want. Yes. Yes, I used it because my starting thing for this is not representations of the Kac-Moody, but I'm thinking of it as operas already. And in fact, I'm even somehow stating that you can work with global operas here. So maybe this is one reason why I want to make sure that this is, to what extent this is consistent. This is consistent with the outline, but I'm not sure it's consistent. So with the outline paper, I'm not sure it's consistent with Dennis's notes. What I get, again, it's the same. It's just int core of log cis on one side and the same source on the other side.
But the DS functor went from KL to int core, and it wasn't equivalence all the time, or it was
Well, again, it was conjectural and equivalence all the time, and this is one reason why I said that I would prefer to work, instead of looking at the run version, instead of looking at factorizable version, just to fix the number of singularities, fix the type of singularities, and consider a very concrete moduli space. The point is that I don't really care about these functors so much. I care only about their images. And if I want to know the image of, say, integration over some space, I'm allowed to chop this space into any pieces I like, because there will be a lone exact sequence, or spectral sequence, I guess. So the result will fit, they will still generate the same category. So for this reason, I'm somehow, well, this is why I wanted to make sure that my notation is consistent, that there are several things you can put here. But as far as the image is concerned, it doesn't really matter. So I want to put something that's as explicit as possible.
So every direct image takes it, preserves in the image we have the conditions and importance of automatic.
I mean, actually, as far as I understand, you even land in quasi-coherent. You're supposed to land in the quasi-coherent part. So.
But you start from
in my notes I started with quasi-coh. I'm trying to match it to what Dennis said, and this does not match. So I want to put quasi-coh here. So this is my secret desire. And to put, but again, this I believe that this is because I'm thinking about finite dimensional situation. I don't want to think about run version. I want to think about the following situation. Let me tell you what I'm thinking about in the case of GLN. So I'm thinking about a vector bundle with a connection, and then you choose a section. And such that if you take this section and start acting by a connection on it, well, you will the result in that this is a cyclic vector. But it's cyclic only generically. So there are some points where this thing will not quite generate your vector bundle. So you need to keep in mind how much how much modification of this vector bundle is necessary. And so I'm considering this space of operas with the extra parameters being the singularity points and the type of modification that is necessary.
So line A was defined in Dennis?
Yes. Well, depends. There was part of it was in Nick's talk. It was defined with the source in Kazhdan-Lustig category, right? And then there was a question of the Drinfeld-Sokolov functor that was relating the Kazhdan-Lustig category and operas. Okay, so I'm sorry if I'm being a little vague here. Part of the reason I'm being vague is because there are several ways of saying, combining the words and getting the same, generating the same category in the end. But so now, what do, Dennis, here you are. So do you object morally to using the so starting with global and ramified operas? Is this something that so using sheaves on global or unramified operas as generators? Say you fix the number, fix singularities, or I mean not fix the number of singularities and type. If you
It's efficient to do that, yes.
okay, and can I consider quasi-coh? Because I put in coh in order to have your.
See, that's an it's an int.
But suppose I fix the type of singularities as much as I can, it will still be an int scheme. Oh, wait. So
That's enough.
yes,
So I mean, if you consider what's called lambda operas,
yes, that's.
that would be fine.
So is it correct to say that the reason you consider int, so your int coh upper star is a poor man's quasi-coh? That the reason you consider int coh upper star is because really it's supposed to be quasi-coh, so the only reason to work with int coh is because it's an int scheme.
Exactly.
And you fix, okay.
So because int scheme, because of these formal directions,
Okay, so I haven't actually.
two lambda operas at distinct points.
Okay, I haven't realized this. So you can. So what you are saying is that it's either I'm supposed to do this or I'm supposed to do this.
Yeah, you could do lambda operas at distinct
Yes.
points, and then quasi-coh is what you want. You got it.
All right. Well. So apparently I shouldn't have tried to fit. Maybe I should try to keep it as simple as possible. And then if I start with quasi-coh, I don't have to think about where this functor lands me. It will land in quasi-coh, and which is embedded into int coh anyway. All right. But now why why are these actually generators? Why do they generate the whole category? So on the automorphic side, so now I have Eisenstein series and I have these strange objects. And somehow the point is that these two boards, these two types of generators are of very different type, so it's sometimes hard to make them work together, but not very hard in this case. So how do we know that Eisenstein series together with this localized guys generate everything? Well, there was a theorem formulated in Nick Stock, so which in particular it implied that if we choose a quasi-compact open inside band, that it's not true that these localizations generate the category, but if we pass, it's only not true because this stack is too large. It's not quasi-compact. If we pass to a quasi-compact open, something of finite type, then they will generate it. So if you restrict to an open, so this is a quasi-compact open, then the image of the composition there are these opers, global and ramified, a bunch of points, types of singularities. So I think Dennis said to call them lambda. So anyway, the image of the composition, so we start here, we go to D modules on band G, and then we go to D modules on band U, not on band U, just on U. So the restriction to U the claim is that the image of this generates the entire category. So this is a statement about Kazhdan-Lustig localization. This is on the one side. On the other hand, we have somehow a very classical statement about automorphic forms. That if you have something that's orthogonal to all Eisenstein series, that is to say cuspidal, then it has to be rapidly decaying. And in this case, the precise statement is that, so this is somehow classical, and in this situation a quite easy result. So if you have, if there is a D module that is such that it's right orthogonal to the image of Eisenstein series functor series, so if it satisfies, so it's home from anything Eisenstein to F is equal to 0. And by the way, by these adjunction relations, this is equivalent to saying that it's orthogonal to anything coming from here. It's the same as saying its constant term is 0. then such a D module is actually exactly extended from a quasi-compact open set U. Well, my G is GL2, so on every component it's extended from a quasi-compact open. And once again, this is a it's a really straightforward calculation. The reason I'm not doing it is because I don't want to discuss cuspidality right now, but it's nice. It's one of the first exercises one should do when thinking about automorphic objects. Then F is equal to, let me just write it, JU lower star, JU upper star F. So in other words, it's, so this where U, running out of room. No, I need this. So, well, I just said it. This happens for some U that's essentially quasi-compact. It's quasi-compact on every on every connected component.
And there's some particular use.
I mean, you can choose some particular U. Is this a question, or are you?
Yeah, it's a question.
No, I mean, but you know this claim, no? That if you have a cuspidal, like you're looking at, yes,
That's a claim for a particular.
yes, it's for some particular U. That there is a nice U where for which,
Easy to say what this
yeah. So past it, everything has to be decomposable.
Yeah.
Right? We're just
Throw away all variance.
yes,
complement to some organization.
yes.
Drakefeld wrote down explicitly in this paper about compact generation of 1G.
But this is GL2 again, so
Oh,
it's
which is GL2, sorry.
yes. So we don't. So it's very easy. It's much easier to say.
This is the same open complexes on which contains support of all cusp forms, right?
Yes, that's the idea I was trying to get across, and apparently failed. Yes.
Then why do you need to restrict to U? I mean, you already get all these U's. If you're,
Well, why do I need restricting to U where?
if you, so there is a U that works for all the cusps.
Yes.
So then
Then what?
why do you need the U?
Can you finish the sentence? I mean, I'm trying to prove basically that a bunch of things generate the category. This amounts to showing that if I have something that's orthogonal to all sheaves in this category, to all the would-be generators, it's 0. So I know that orthogonality to Eisenstein series forces my thing to live on a compact open. And I know that on a compact open, on a compact open, these localized guys detect everything. This is the statement.
Well, do we need orthogonal from one side, not from the other?
From one side. I mean, this is the way these things work when we say generate. So now this has two equivalent meanings. Either you say that everything is a direct limit of these guys, or you say that it's a right orthogonal in this order.
I'm still a bit confused.
Yes.
You get all the Eisensteins without U, right?
I
So the two sets of generators generate everything you don't.
No, it's not the Eisenstein series that satisfy this property. It's the orthogonal complement that has this property. So this says that the orthogonal, if F is orthogonal to Eisenstein, then it sits on finite, it's quasi-compactly supported. Yes. So Eisenstein series can be used to generate everything at infinity and maybe.
Why do you need in that theorem a U? Why doesn't it work for a connected component?
Because connected components are not quasi-compact. This is not Picard.
I understand they are not quasi-compact, but why doesn't it work, the theorem, on a connected component?
Which
The
theorem?
that you said it, A theorem, it implies.
What do you want me to say? You want to change its quasi-compact open on each component?
Yeah,
What? No, I just don't understand what. Yeah. No, I mean, okay, I think now I understand. My problem is that I chose G to be GL2, so it has infinitely many connected components. So I cannot just, and it's not true, so I say this for some U that's quasi-compact on every connected component, simply because it's not true that cuspidal thin has quasi-compact support. It's true that it has quasi-compact support modulo something. Does that make sense?
Yes, but
Okay, anyway, we can talk about it later. So now, so this is what happened on the automorphic side. Now, what happens on the Galois side? Now, so now on the Galois side, we have to combine two results again. So one of those results appeared in Dennis's talk, which so the result about well, that in the case of GL2, it simply says that all I need to know is that every reducible local system admits an OPER structure with singularities. So in other words, I'm saying that in this correspondence, there is actually a way to write a system of two differential equations as a single order two differential equation. And hopefully this is something we believe in. And so this result, now I lost my eraser. And so on the Galois side, we again need to combine two things. So first of all, there's a following result, which is classical and easy for GLN, and then I'll still open for arbitrary reductive groups. If it's not, the group is not classical, is that this map V is surjective if singularities are sufficiently so if we choose sufficiently many points and sufficiently high order of poles for these OPERs, then the forgetful map is going to be surjective over the irreducible locus. So for large I and large lambda, just for some I. So this is on the one hand, and on the other hand, the claim is that from the theory of singular support, we can check that it's in fact quite easy to check that the image of the Eisenstein series functor, I'll uncover it in a moment, so the image of this spectral Eisenstein series functor, in fact, I can tell you exactly what this image is. So it lands in int core. And I claim that its image is characterized by the following singular support condition. It's given by the condition that the singular support is contained in the nilpotent cone, but only in the nilpotent cone over reduced local systems. Reducible local systems, sorry. So let me try to somehow make sense of this. So these are my functors, and I am talking about the following. Here's what I am saying. Sorry? On reducible local. So I consider local systems that are reducible, and so let me try to draw a picture. So here's what. So there is this. This is my picture of the stack of local systems. Over this stack, we can consider its sing, but I actually never have to work with the entire sing. I'm only interested in the nilpotent cone. So let me just draw a nilpotent cone instead. So this is nilp sitting in sing. So this sits in sing of ls chit-chat. So what does it look like? Well, it's over some systems it will be 0. Over some you will get more. You will get some kind of nilpotent cone sitting. Right? Now, local systems could be reducible or irreducible. There's a closed locus of reducible local systems. So these are, let's say, reducible. And despite appearance, this is supposed to be closed in the Zariski topology on this line. So these are reducible local systems. And then there's the open locus of irreducible local systems. Now, I claim that, so it's only reducible systems are allowed to have nilpotent cone, because nilpotent cone is about endomorphisms. And so I guess Schur's lemma. So I claim that everything with support here so this is where, well, it's kind of clear that if you apply Eisenstein, this spectral Eisenstein functor to anything, its singular support will land on this, will land here. You cannot get anything irreducible by induction from Borel. What is the non-trivial part of the statement is that you in fact generate this category completely. So this is somehow the thin supported here is the spectral counterpart of category of Eisenstein series. Right? And then the claim, this generatedness result, simply says, well, if I have anything sitting on this locus, I can look separately at the part supported this part and the part sitting over a reducible part. Here I have Eisenstein series, here operas do the job. Does it make sense? And so let me just, so hopefully I explained where the generators are coming from. Now, at least in general words. Now let me, it's time to finish, so let me just say what's involved. Now the last part. Yes.
But there was this
Yes. Yes. So this picture is somehow accurate in the way that we might be actually also sweeping some local systems that don't actually have any nilpotent.
But then, it doesn't contradict.
Yeah, it doesn't. Yeah, we're just generating even more than we.
No, I don't think it's reducible. So you take two direct sum of E1 and E2, which is only symmetric, there's no single support.
Yeah, that's okay.
Well, there is sync, but no nilpotent cone.
There's sync, but not important.
Yes.
That guy is like extension of trivial by trivial.
So Poincaré spectral parallaxes generate reducible.
Yes. Yes. So Eisenstein series is really, in this spectral Eisenstein series, are literally just thin supported over reducible local systems, and so cuspidal is literally the. Somehow the cuspidal category is the quasi-core of irreducible local systems. All right, now let me just say a few words about what's really involved in matching the images of these two sets of generators. And I almost said this already, so it's match the images of generators in their respective Whittaker categories. So in other words, matching the Whittaker coefficients of the generators. So, technically I'm supposed to match somehow their extended coefficients, so I'm supposed to look at non-zero coefficients, the zero coefficient, and the gluon map between them. So, and just in a few words, for Eisenstein series, this is reasonably, well, this is technical, just because the objects involved are somewhat unusual, but essentially supposed to be a geometric calculation. Now, so the kind of calculation involved, for example, what do we need to do? For example, we need to start here, apply the Eisenstein series functor, and ask what the constant term does to it. Or start here, take Eisenstein series, and take its Whittaker coefficient. So we can have to do this on spectral side. We have to do it on both sides of the correspondence and compare the results. So this is not 100% finished, partly because in order to compare the results, the bottom rows should be matched perfectly, and this is well, there are still some subtle points there. So now, but at least in principle, it's clear how to go about doing this. And now the second type of generators, the uppers. How am I supposed to pronounce this? Uppers. Anyway, so for this second type of generators, it's hard to do this geometrically because they're not very geometric. They are like D-modules. So on the geometric side, they look like D-modules with given by certain generators and relations. Fortunately, we know just enough about them to make this work. On the one hand, we have this fundamental diagram. So the fundamental diagram basically allows you to match their non-degenerate coefficients. So this is somehow the meaning of the fundamental diagram. Match non-degenerate part. And after this, it's kind of tempting to say that, well, since we already matched the Eisenstein series, and if we also know that the non-degenerate parts match, the categories should be the same. It's a little more subtle than that. In fact, there's a second important part in this story, namely we need to know that we need to know that the algebra of the action of the Hecke algebra on these guys is compatible. So if we also use the action of the Hecke algebra, I just want to say that the two things that go into the proof are A, the fundamental diagram that was formulated in Dennis talk, and 2, compatibility with the action of the Hecke. These are the only things that we need to know about opers to make, well, for things to work. So I think I should stop here.